So this talk, titled Improved Hardness Result for the Guided Local Hamiltonian Problem, is based on two separate archive submissions. One by Sevag Gharibian, who's sitting here, Rio Hayakawa, who's going to be presenting the second half of the talk, Francois, Gall, and Tomoyuki Morimae, and another one by Cade, who's also here, Marten, Folkertsma, and myself, Jordi. So the main motivating theme for this work was to study the idea that quantum chemistry, or say quantum many-body physics, belong to the most promising applications for quantum computers. And perhaps the most central computational task in this field is the one of ground-state energy estimation, which informally reads as follows. You're given the classical description of a local Hamiltonian H, and your task is to compute its ground-state energy up to inverse polynomial precision, or let's say accuracy delta, additive error. And recently, Lee and others, they formulated the idea that this perhaps may be done exponentially faster on a quantum versus a classical computer as the exponential quantum advantage hypothesis for quantum chemistry, which reads as follows. For a large set of relevant generic chemistry problems, the ground-state energy estimation problem may be completed exponentially more quickly as a function of the system size on a quantum versus a classical computer. And of course, an intuition that one might give to justify such a belief, if one believes it, is that of course the systems you're trying to simulate are themselves quantum systems, so may perhaps be modeled or simulated more easily on systems that themselves are governed by the same physics that you're trying to model. However, Lee and others show in their work, they give numerical evidence that perhaps classical algorithms that can really long back on a very long time or very successful studies and improvements are already very good in terms of scaling and solving these problems. But we were interested in the question whether, if one would believe such a statement, one could also provide some rigorous footing to it to justify such a belief. And to study this from a complexity theoretic perspective, it might be helpful to first formulate the problem as a decision problem. The local Hamiltonian problem reads as follows. You're given a classical description of an Hamiltonian H, which consists of m local terms, each of which acts at most k qubits at the same time. Then you're also given two real numbers, a and b, of which the difference is lower bounded by some parameter delta, which is strictly positive. And then your task is to output yes, if the ground-state energy, which will be denoted here as lambda subscript 0 of h, is smaller than a, or you output no when it's greater or equal than b, if the promise that either one of those two is the case. And it's already very well known for a long time that in general this problem is QMA complete. Already for k greater or equal than 2, and when the desired precision is on inverse polynomial, has been shown by Getachew and improved by others. So there's no hope of solving this problem in the most general case, even for quantum computers. So one might wonder, can one impose other constraints on a problem or on a Hamiltonian to maybe make the problem easier? Well, in general, the answer is maybe that's not the case. So it's already known that on a 2D lattice, the problem remains QMA hard. If you have interacting bosons or fermions, it's maybe more physical, it remains QMA hard. And also for supersymmetric systems, still QMA hard. And there are many more of these results out there. So is there then no hope in that sense? Well, there are also results that show the problem can in fact become easier if you allow for additional constraints. So the stochastic filtration-free Hamiltonian is MA complete. Diagonal local Hamiltonians are NP complete. And the problem is even in P when you allow for one local Hamiltonians. But if you want to show a quantum advantage, then actually from a complexity theoretic perspective, you would hope to show that the problem is actually in some kind of modification, some kind of different version of it, becomes BQP complete. Because then it would precisely characterize the power of quantum computers. For this, let us first get some inspiration from what was proposed in practice over maybe 30 years. So when we have fault-tolerant quantum computers. One should adopt the following two-step procedure. First, one uses a classical heuristic to obtain a good guiding state, some kind of trial state, which is hoped to have good, and with good meaning some inverse polynomial fidelity with the ground state or the ground space of the Hamiltonian you're interested in. And then what you're going to do, you're going to get the state and prepare it on a quantum computer, so this should also be possible. Then you're going to run quantum phase estimation to project them to the ground state and estimate the ground state energy up to high precision. And since these guiding states come here from a classical heuristic, they need to have a classical description as well. In this talk, we will consider ourselves with the following set of states, which can be viewed as a uniform superposition over a polynomial number of basis states that then have applied isometries to the single qubits that map to a constant number of qubits. And notice these are just these polynomially sized subset states, and these isometries are just identity for every I. And let us now focus on only the second of the complexity of only the second step of this procedure. So the guided local Hamiltonian problem, introduced by Francois, Gall and Gharibian last year, is just as the local Hamiltonian problem, but it differs in the way that you actually get one of these guiding states as part of the input. So you get the semi-classical encoded quantum state U as part of the input, and then you have the promise that actually the fidelity of the ground space of this guiding state is lower bounded by some parameter zeta, which also then comes into the definition or the description of the problem. And what they showed in their work was actually that you have BQP completeness results for the guided local Hamiltonian problem in the precision settings of for delta some inverse polynomial when the locality of the Hamiltonian is greater or equal than 6. The fidelity zeta is 1 over poly or at most inversed polynomially close to a half. And they also showed some classical containment result. In fact, under L2 norm sampling assumptions to this guiding state, you can actually show that the problem is in BVP, so classically solvable. So the precision really plays an important role in the complexity of the problem. However, some natural questions might pop up looking at these results. So I already told you that the problem is QIP2023 for the locality greater or equal than 2. And here we only have 6, so this differs from the QMA setting. So one might wonder, what about k greater or equal than 2? Furthermore, the Hamiltonians considered in the proof, these are not very physical Hamiltonians. So I mentioned at the beginning this exponential quantum advantage hypothesis, which says that the Hamiltonian should be generic. Even though it's not very clear what it means to say that the Hamiltonian is generic, as physicists like to say, we think that at least it means that the Hamiltonian should come from a family of Hamiltonian that's actually closely related to physical systems. Furthermore, what if the fidelity promise actually becomes larger than a half? Becomes a problem then easier, like classically solvable? And what about excited states? Do ground states really play an important role here? In these works, we further generalize the guided local Hamiltonian problem, which now only differs from the guided local Hamiltonian problem by having another input to the problem, which is a label C, there's some natural number. And this label C indicates the number of the excited state that you're interested in. So note that if C is 0, then it's just the old guided local Hamiltonian problem. And again, we have the promise that, so you want to estimate the energy but now of the excited state. And again, you're giving just a guiding state, but now it has some promised overlap or fidelity with the corresponding eigenstate of this excited state. And besides that, the problem is just the same as we had before. And in these works, we show, again, BQP completeness results, but then for this guided local Hamiltonian low energy problem, again in the regime for an inverse polynomial precision, when the C is upper bounded by some polynomial in n, so the number of qubits the Hamiltonian operates on, which is a new result. The locality can be greater or equal than 2, which is an improvement over the previous result, and it is optimal. And the fidelity can be 1 over poly, but also inverse polynomially close to 1, which is an improvement and also optimal. And the star here indicates that for excited states, the containment is slightly different, but we will not go deeper into that for this talk. But for ground states, this will hold for containment. And we also show that the result holds for physically motivated Hamiltonians. And Ryu will explain which ones these are. So for the second half of the talk, Ryu will take over. And to display all the used techniques in getting to these results, he will sketch a proof that combines all the aforementioned results together in like a single result. So to be slightly more precise, he will show a theorem about estimating the sieve excited state energy of a physically motivated two-local Hamiltonian up to inverse polynomial position, given a guiding state that has inverse polynomially close fidelity with the corresponding sieve eigenstate is in fact BQP-hard.
Okay, can you hear me? Okay. So let me proceed with some technical parts. So let me first give the overview of the proof, which is guiding information of the proof. So first, we reduce the BQP decision circuit to a first GLH instance, which is given by a 5 local Hamiltonian H1 and the guiding semi-classical subset state U1, which is promised to have a 1-1 over poly overlap with a ground state of H1. Here, we use a variant of circuit Hamiltonian construction and a perturbative analysis of the ground state to show the BQP hardness. And then we use a so-called excited state gadget to obtain the GLHE instance, which is given by 6 local Hamiltonian HC and the semi-classical guiding subset state U2. And this U2 is promised to approximate the cis excited state of HC with 1-1 over precision. And then we finally apply a chain of perturbative simulations to obtain the two local physically motivated Hamiltonian and the corresponding semi-classical encoded state U3, which can approximate the cis excited state of physically motivated Hamiltonians. And the physically motivated Hamiltonians relevant to the BQP hardness results are the following Hamiltonian family of Hamiltonians. And first is the XY Hamiltonian defined on a 2D square lattice of this form. And the second one is the anti-ferromagnetic version of XY Hamiltonian defined on 2D triangular lattice. The anti-ferromagnetic means that all the coefficients of Jij's are all non-negative. And the third one is the Heisenberg Hamiltonian, which is defined on a 2D square lattice of this form. And the last one is the anti-ferromagnetic version of the Heisenberg Hamiltonian, defined on a general graph. So we have shown the BQP hardness results of estimating the excited states for those two local Hamiltonians. And so I proceeded to show how we obtain those improvement compared to the previous results. First, I explain how we obtain the improvement of the overlap with the guiding state. So let UX be a quantum circuit that can decide the BQP problem X. So the UX may look like this, and by applying this UX to some initial state, and by measuring the output qubit of this circuit, this will output one with high probability in the yes case, and this will output one with very low probability in the no case. And we first modify this circuit UX by adding the pre-idling. Pre-idling means to adding the identity gates. So this does nothing. And adding identity gates before quantum computation UX. And we apply a circuit Hamiltonian construction for this U tilde X to obtain the first Hamiltonian H1 of this form. And we can analytically show that for the first 3 terms of this Hamiltonian, this part has a unique ground state, which is given by the so-called history state. And we can also show analytically that this part has a 1-1 over poly gap. Therefore, we can use a perturbation theory to analyze the actual ground state and ground state energy of H1. And we can take polynomially large enough delta and take a polynomially large period of pre-idling steps. So by taking such proper parameters, we can show that there is a 1-1 over poly overlap between this history state and the ground space of H1. And this history state can be approximated by this semi-classical subset state. So this is a subset state. And this also has a 1-1 over poly overlap by taking the long idling periods. So this can be work as a guiding state for this H1. And we can also show that the ground state energies of this H1 in the yes and no cases have 1-1 over poly gap in the yes and no cases. So this GLH problem can be used to decide the original BQP problem X. And then I proceed to explain how we obtain the excited state Hamiltonian. Here, we construct HC in this way. And Hz and Hs are the Hamiltonians. They which have energy spectrums like this. And Hz is a Hamiltonian which have a gap. So the lowest energy of Hz is minus c plus 1/2, and this has a precisely gap by one. And the spectrum of Hs can be obtained by somehow normalizing the H1 which I've already obtained. So that's the energy spectrum lies between -1 quarter and 1/4. And the spectrum of this Hc can be obtained by combining those two spectrums. So it can be seen that the cis excited state of Hc corresponds to the ground state of Hs, and this is the cis excited state of this Hamiltonian, and this can be approximated by the new semi-classical subset state U2. And this is how we obtain the excited state Hamiltonian. And then I finally explain how to obtain the two local physically motivated Hamiltonians. Here, we apply a series of perturbative simulations to reduce the locality and finally obtain the physically motivated Hamiltonians. There are two requirements that for the BQP hardness results to be false. First is that the energy spectrum of the original Hamiltonian must be preserved in some way. So in the Hamiltonian simulations, the original energy spectrum of the original Hamiltonian is encoded in the new Hamiltonian in below the low energy subspace of the new Hamiltonian, and the energy spectrum is preserved with some small errors. And so the first requirement can be satisfied because those families are known to be strongly universal. This strongly universal means that those target Hamiltonians can simulate any order 1 local n-qubit Hamiltonians efficiently up to polynomially large parameters of Hamiltonian simulations. And the second requirement can be satisfied because only local encodings that preserve the semi-classical property appears. So we can encode the guiding state of semi-classical guiding state of Hc into the another semi-classical guiding state of physically motivated Hamiltonians. To be concrete, let's start with semi-classical subset state U3 and the kind of encodings that appear in the Hamiltonian simulations are as follows. So we attach polynomially many some simple ancillary states first. And those are called mediator qubits in the literature of Hamiltonian simulations. And then finally, we apply some local encodings that is given by a tensor product of local isometries. So therefore, the resulting state is a semi-classical encoded state. So therefore, we can obtain the description of physically motivated Hamiltonians efficiently, and also we can efficiently obtain the description of semi-classical encoded state. So this is how we obtain the BQP hardness results of two local physically motivated Hamiltonians. So let me conclude our talk by giving summary and conclusions. In the previous results, BQP hardness results were shown for 6 local Hamiltonians, but the locality and the approximation parameters were not optimal. And it was not known whether this whole results holds for physically motivated Hamiltonians and the excited state energies. So in this work, we have optimally improved the locality parameters and the approximation parameters from 6 to 2 and 1/2 to 1-1/3. And we also show the BQP hardness results for excited state energy estimation problem and the local physically motivated Hamiltonians. And as a future directions, one important direction is to show the average case classical hardness results for the guided local Hamiltonian problem. And second one is the important one is to improve the promise gap from the current 1 minus 1 over poly to 1 over n, which is a precision in the quantum chemistry. So this is at the end of our talk. Thank you for listening.
Hello, thanks for a nice talk. And in your talk, you mentioned a special class of Hamiltonians called physically motivated Hamiltonians. What's the definition of the class, and what's your motivation for considering the class?
Yes, actually, there is no. I think there is no rigorous definition what is a physically motivated Hamiltonian. What we wanted to do is to getting the family of target target families to getting closer to the Hamiltonians that appear in quantum chemistry. So yeah, and we hope that the results of Heisenberg Hamiltonian or something is closer to quantum chemistry compared to the previous results. Anything to that? Okay.
I have a question here. So I have a question about your second bullet point. So yeah, as you guys alluded to, you're motivated by this quantum chemistry question, and I'm not a quantum chemist, but I hang out with quantum chemists sometimes, and they really care about this setting where the additive error in the ground state energy is a constant when the Hamiltonians are normalized, so which is this 1 over n setting. Do you guys have any thoughts on this? Like, will it turn out to be BQP complete, or is there some barriers to proving this is BQP complete? Like, what's going on? Do you have any intuition?
Right? Yeah.
Yeah, so any thoughts? So mainly like we use the circuit Hamiltonian mapping in the beginning here to go from a circuit to a Hamiltonian construction. And already there you don't have this gap appearing. So I think if you do the circuit Hamiltonian mapping, the Feynman-Kitaev in the normalized setting, you've already that it goes with 1 over L, but it's unnormalized. So if you normalize, you get, I think, in this case, an n squared. So you really need to get a new technique here, or really show that like maybe that the actual ground state of the circuit Hamiltonian mapping actually maybe has this energy, but this is really unknown. So or we need a new technique, or we need to study the current technique better to get to this.
Yeah, thank you for a very nice talk. My understanding of these perturbative gadgets is that if you're trying to reduce the locality from with these perturbative gadgets, you can sort of induce some exponential blow up in the interaction terms, and that's okay when what you're trying to prove is QMA hardness. But I would imagine that it's a problem if you're trying to show BQP completeness. So how do you did you encounter this problem, and how do you avoid it?
Sorry, you mean that there is an exponential blow up in the energy in this contraction?
When you use these perturbative gadgets in the sort of interaction energies for the new sort of simulator Hamiltonian.
Yeah. There is only a polynomial blow up because of some technical. Because we.
So is this where you're using this strongly universal simulators thing from Aronoff and Joe?
Yeah, that means that. I see. That strongly means that there is no such exponential blow up. So we can modify the quantum circuit in some way that is a sparse. Yeah, we can change into some sparse circuit, and the sparse circuit there is no such exponential blow up.
I see. Okay, thank you.
So maybe I have a final question. So do you know what's the complexity of deciding if there is somehow a short description that overlaps with the ground state? Like, is there, like, should it be QCMA hard or something? Like, this is a promise for you, right? So what if I want to remove the promise and I want to study the complexity of finding if such object exists?
So if I understood your question correctly, you're asking what's the complexity of getting basically such a guiding state?
Yeah, exactly.
Or, yeah, it's actually maybe a good question for future research we're also thinking of. But I mean, it's at least QMA hard, right? Because if you have this description, you can, if you can get the guiding state, you can also solve the decision problem of the ground state energy. So it's at least QMA hard. But
okay. is it quick? Like,
So just to be clear, you introduce a guiding state to make the quantum treatment easy, but are you convinced that the classical treatment remains hard if you have that guiding state?
Yeah, so that's also related to the previous work. So the previous work uses L2 norm sampling to get like a classical containment result. And this state that we actually use can still be L2 norm sampled, so you can still get the same classical containment result for these states. So that also goes through.
oh, I see. So yeah, we have to finish this talk. Maybe you can ask more questions offline. Thanks, Hphys, again.